Welcome, this is Algebra 1, Semester 2, Unit 9, Section 10.1. This is the very beginning of this unit. This is page 1 of the packet. You can see we have a lot of sections. This is a very important unit. This is quadratics. Please try to be in class for this. On page 2, you'll notice the vocab, just like normal. I just put them in order matching so that you can choose whether to do an audio recording, flashcards, or whatever. Just list them A, B, C, D, E, F, G. That is the order that they're in. On the test, they'll be all scrambled up for you. Okay, first thing we're going to do here is piecewise functions. Piecewise functions is simply putting pieces of graphs on the same grid. I'm trying to fit this in the window there. I think that's pretty good. So you notice over here we've got an f of x. Remember, that is simply the function name for y. You can switch that back if you're more comfortable and make it y equals -4. Or on the bottom one it would be y equals -2x plus 8. The other option, if you're kind of getting ready for pre-cal and all of that, you could just come over here and label this as f of x and begin thinking about your graph truly being x and a function of x. Okay, so here we go. When we graph y equals -4, as we've reviewed in the past, when you have one letter and a number, you simply are cutting through that axis. So we go to our y-axis and we cut through at this -4. 1, 2, 3, 4. Now, when you draw this line, because you're doing piecewise graphing, please draw it really light. Very lightly, just right across that graph, just to know where it's at. And make sure you're not using ink. If you are, stop and get a pencil. Now, we look at the window. Right here, I give you a window of what I want to see. I say when x is less than -3 or equal to -3, that's all the more of this line that I want to see. So come to your x-axis, -3 is right here. And I am saying I only want to see when it's less than that or equal to it. So come down to the line, put a dot on -3, darken this side of it, darken the arrow tip, and then erase everything else that's not in that window. That is the piece of graph that I want on this piecewise function. Okay? Your next one, it is -2x plus 8. Ooh, I may have ran that off the graph. 1, 2, 3, 4, 5, 6, 7. I did. Let's switch that. We'll just count that as a typo. I'll try to get it corrected for yours. Let's switch that to, let's say, 3. So -2x plus 3. To graph that, you will come over here and go to +3. That's your y-intercept. Now you are going to rise 2 and run 1 to the left because it's a negative. So from that point, you're going to rise 2, run 1 to the left. Now lightly draw in your line. And we look here and I say from the window x is greater than or equal to 1. So we go to where x is 1. And we have to show just that side of it. So we come up and we put a solid point there showing that it could be equal. And then we simply darken from there to the right of there because that's greater than. And I erase everything else. So there's piecewise functions. Basically, you're taking the equations given, graphing those lightly, and then adjusting for the window, darkening for the window, and erasing what's not in that window. Okay? Go ahead and do this next one on your own and then turn it back on and see if you have it correct. There's the second piecewise function. See me in class or talk to another student if you had some difficulty on that. How are piecewise functions and step functions different from other functions? Well, piecewise functions are pieces of functions. Step functions are pieces that look like this. They'll go up like this. They look just like a step on a graph. And they're usually equal intervals the whole way up. Okay, and they're pieces as well, but they're always horizontal steps, so very useful in graphing. Okay, in this section, what we want to get to are translations. Translating of the quadratic graph. We call this a parent function because it has no numbers in here to change the shape of just a very basic quadratic shape. Okay, so we go ahead and we plug in numbers. If we plug in 0 for x, at 0, 0 squared is 0, so our point is 0, 0. And we put the point right at the origin. Now if we plug in 1 for x, 1 squared is 1, so we would have 1. In addition, if we plug in -1, -1 times -1 is 1, so we would have 1, 1, and -1, 1. If we plug in 2, 2 squared is 4. In addition to that, -2 times -2 is 4. So out here at 2, we come up to 4. Okay? So now you just smoothly draw in that U-shaped curve that you're getting with a quadratic. And that is the shape of your parent graph. Okay? Now, everything that we graph today will be a transformation of that parent graph. We're going to look at what other values do. See the parent graph in here? We can kind of spot. We have the y, and we still have the x squared. But we can place numbers in here that make some shifts to it. We could put a positive or a negative out front. Well, it actually has a positive. We could replace that with a negative and see what that does. We could also put a number out front, see what that does. We could put a number in here beside the x inside the squared. That will have an effect. Or we could put a number after the square. Okay? So we're going to play around with all those. First one, let's just play with the negative out front. Let's just make that little switch. Let's say we have -x squared. Now, I want to switch back to my pencil. Never ever graph with a pen. Need to be able to erase. Okay, so if we plug 0 in, 0 squared is 0 times a negative is 0. So we still go through the origin. No change there. Let's plug in 1. 1 times 1 is 1, but now we multiply by a -1. Or a negative out there, so it becomes a -1. -1 times -1 is 1 times a negative is -1. Ooh, so what happened on those points is instead of going up here, they're down here. If we plug in 2, 2 times 2 is 4, times a negative is -4. Same thing happens to our 2's. So when we graph those, we see clearly now what the effect of that negative out front is. If we look at where our parent graph lay, it was up like this. Now we've shifted it this way. What this negative does, it causes a reflection. It's a reflection across this x-axis. Anytime you see a negative, it's going to flip it over that horizontal axis that its vertex is on. Okay? Well, here we go. Now we have a parent function, and we're going to want to play with the a value that we talked about being out front. We want that a value more than 1. So let's just make it, let's see, 2. Oh, let's go with, yeah, let's do 2. So we have 2x squared. So now we think about our parent function. We can graph it from just looking up above. When we put a 2 in there, we see that 0 times 0 is 0, times 2 is 0. So the origin, or the vertex, has not shifted. The turning point of the graph, the vertex is still the same. If we put a 1 in there, 1 times 1 is 1, times 2 is 2. So we just lifted that point that was at 1, 1 up to 1, 2. We've stretched it up away from that x-axis. And as I showed you, negative 1 times negative 1 is 1, times 2 is 2. Now we go to 2. 2 squared is 4, times 2 is 8. So that takes that one clear up here off of our graph. So when we change that a value to something bigger than 1, it stretched it. Stretched it off the x-axis. Now again, we just think about our parent graph. That's what we're always comparing to. Go ahead and plot it in here from memory. Now, what will happen if we switch that a to being a fraction? Let's say that we have a really, really wide fraction. Let's say we go with 1/5, okay? X squared. So, if we plug in 0, 0 times 0 is 0, times a fifth is 0. So we haven't changed our vertex. It's going to still be on that point in the graph. But now let's look at 1. 1 times 1 is 1, times a fifth is 1/5. It barely comes onto the graph. Negative 1 times negative 1 is 1, times 1/5 is 1/5. So we see that it's still symmetrical there. 2 squared is 4. 4 times 1/5 is 4/5. Same thing for negative 2 would be 4/5. So we end up out here at 2, barely at 4/5. Let's go clear out to 5, because I'm a little bit worried trying to graph this. Let's say that we plug in 5. 5 squared is 25. 1/5 of 25 is 5. So finally out here, 1, 2, 3, 4, 5, we go up to 1, 2, 3, 4, 5. Wow, pretty wide parabola then. So we see how it's going real wide compared to that parent graph. Instead of being stretched up off the x-axis, it shrinks back down to the x. So we call that a shrink of 1/5. Okay? Next graph. Go ahead and fill in the parent function. That's what we always compare to. Okay. Now we want to see what happens if we add a number out there. If you remember right from page 1, that was called a k in our formula. So let's just say we have x squared plus 2. Okay? Well, if we plug in 0, 0 squared is 0 plus 2 is 2. Oh, so it moved our vertex off of that origin up to 2. If we plug in 1, 1 squared is 1 plus 2 is 3. Negative 1 would also be 3. 2 squared is 4 plus 3 is 7. That's going to take us clear off the graph. So now you notice we didn't make it wide, we didn't make it real skinny, but what we did is we took that parent graph and we just shifted it up the number of places that that k value was. So k shifts it up. With this many skills, I was thinking that we could answer a question from a standardized test. It says, can you determine the equation of the quadratic function by looking at the graph? Well, it's upside down, so we know that it's got a negative out front, correct? We know that it's some kind of an x squared shape because it's a u shape. But do you see how it's shifted down to? Well, this one just now shifted up to. So does it make sense that it would be a k value of -2? And we find our answer right there in C. Okay, next page, this is page 6 of the notes. Going to do a few more transformations and then we're done here. Go back to our parent graph. We always compare to it, that's why I keep having you draw it so that you'll get it in your brain. So there's our parent graph. Now we want to look at a shift of a minus k, which you just saw in the standardized test. So feel free to go ahead and graph this and then turn it back on and see if you've done it like I did. I chose the equation x squared minus 3. So at 0, we're down at -3. At 1, it's -2. -1, it's -2. At 2, it's 1. So what we notice happened with our parent graph, there's our vertex, and now it goes over and it shifts down the number of k units that we went minus. So, kind of neat. Now we want to look at transformations if we have the value inside the parentheses. We call that a minus h value. So let's just say that we have an x minus 4 squared. Okay, our parent graph again was 0, 1, 1, 2, 4. So it's going like this. Well, if we put in 0, 0 minus 4, that would be -4 squared would be 16. That thing's off the graph. Wow. If we put in, gosh, let's see. Let's try to get it to 0. 4 minus 4 would be 0, so let's put in a 4. 4 minus 4 would be 0. Now let's work from there. 1, 2, 3, 4 is 0. Well, 5 minus 4 would be 1. 1 squared is 1. So now we have 1. Let's see if this 3 is 1 as well. 3 minus 4 is -1. -1 squared is 1. So we do have the shape going up right here. If we go out to 6, 6 minus 4 is 2. And 2 squared is 4. So at 6 we're up 4. At 2 we're up 4. So we see what we've done to that parent graph with the -4 being in there. Isn't that interesting? It shifts 4 to the right. It looks like it could possibly go 4 to the left, but not to the right. Why do you think that is, that we have a -4 and it goes +4? It has something to do with this formula. So I'm going to ask that in class tomorrow. See if you have a good guess. Why is this causing it to go to the right? And it has something to do with the formula. Okay, the last standardized question here, looking at the graph, it says, choose which transformation equation this is. Well, we see the origin has moved from, the vertex has moved from the origin. It goes over 2 to the left, and then down 1. Well, we know that that k value is what made it go down, a minus k out there. So we have a -1, a -1. Here we have a +1. We know that that can't be right. Eliminate it. Elimination in math on multiple choice is an excellent technique. This one is a -1, so those are all good. Now, what are the differences in these equations? Well, here we see a minus out front. Remember, the minus out front made the parent graph turn upside down. Is this graph upside down? No. So let's eliminate that one. So now we're looking at this. The only difference is this is -2, that's a +2. So let's go back to the one we just did. When it was -4, it went to the right 4. Well, we're going to the left. So if -4 made it go right, then I would guess that if we want to go left, we need to have a +2. That's a guess right now because we haven't learned it, but it might be a good guess. Okay, next graph. We're actually going to put a positive in there now. Let's just do what we were just asked. X plus 2 squared. Okay, first we want to set up our parent graph. And now we come over here and we say, okay, we're going to add 2. What would make this 0? That's the first thing I'm going to look at. If I put in a -2, -2 plus 2 is 0. So I have my 0 at -2. Now, let's go right next to there. Let's go -1. -1 plus 2 is 1. 1 times 1 is 1. So that leads me to think that -3 would also be 1. -3 plus 2 is -1. -1 times -1 is 1. My guess is at 0, we're going to go up to 4. 0 plus 2 is 2, squared is 4. So there's our parent graph. And as you notice, we simply shifted that parent graph, the vertex of the parent graph, we just shifted it to the left when we put a +2 in there. Okay? Can you determine the domain and range of a quartile function? Well, we didn't happen to look at domain and range here, and we do need to go back and talk about those. So let me grab these sheets real quick, and let's just put our domain and range back into them. If you would turn to page number 4, and we'll look at the reflection first. Domain and range is saying, what are my limitations on my x and y values? Well, my x value, that's going this way across the graph. As this u spreads out, there's no restriction on the domain, on the x values. X is going to be all real numbers because it can be anywhere along there. But the y, if you notice, the range is your y-axis. There is a limitation. This is your reflection. This was just something that I was having you think about. But this is the actual graph down here. There is no graph above 0, is there? So y is less than, it can be equal to 0, but it's only less than 0. Going to the next one. See how the domain again is unrestricted, because as this u goes out, it'll cover all these x values out here. As the u goes out, it covers all the x values out there. So the domain is all real numbers. The range, however, again has a restriction. There's no graph down in here. It's only from 0 up. So y is greater than or equal to 0. Okay. Looking at the next graph on page 5, again, domain, all real numbers. Because it goes to the left or the right as far as it wants to, well, forever. It's infinite. On the range, however, no graph, no graph, no, we see graph right here. That's the first point. Y is greater than or equal to 0. Now that isn't how it will always be. Take a look at this one. Where does the graph start? At 2. So in this case, the range is y is greater than or equal to 2. The domain is still all real numbers because it can go to the left and right as far as it wants. Okay, on page 6, go ahead and fill in this domain and range, and let's see if you have it right. Pause the video. The domain is all real numbers, but the range is y is greater than or equal to -2. Okay? On this one, domain, all real numbers, y is greater than or equal to 0. And again, that's the range. So now it says, which of the following equations has a range less than -3? Well, that means that the graph is down here at 3, and it's coming down this way, isn't it? Because it says it has to be less than 3, less than -3. So let's eliminate things. First off, we know that it's got a negative out in front of that x squared for it to be going down. This does not have a negative out front, eliminate it. This does not have a negative out front, eliminate it. What is the difference between these two answers? Well, one is up here at +3, that's a k value, so we know that that graph is looking like that. This graph is down at -3, and we just said because the range was at -3, it was from here down. So that means the +3 is out, and our answer is B. Okay, the function y equals x squared is translated 5 units left. Well, we know that in our equation, the plus minus a, x minus h squared plus k, that it was the h that made it go left and right. I remember that when it was at a -3, it went +3 on the graph. So if it's going left 5, I know that that's the opposite of what it looks. So it would be x minus from the formula a -5, which makes that x plus 5. That's why it looks opposite. And then it's going to go down 4 units, -4. Doesn't say anything about it being stretched or flipped upside down. So the first thing, you're comfortable knowing this down 4 units. I would eliminate anything that's not down 4 units. That leaves you with this and this. We just deduced that the reason that the left and right shift is opposite is because of that negative in the formula. So, since it's left 5, it's going to look opposite. Left is normally negative, so it will appear to be positive. That's the end of that unit. Thank you very much. We'll see you tomorrow in class.